welcome to week 9. This week we are looking at some applications of double integrals. While initially on the syllabus it says we were supposed to spend the entire week on applications of double integrals to save some time and also give us some space at the end of the course, I've decided to briefly look at these applications and then look at triple integrals a little earlier. It gives us a little extra space here at the end of the course. While there are many applications of double integrals, the two that we're going to look at here are using double integrals to find centers of mass and to find surface area. I'm not going to prove these formulas, but I'll kind of give you a rough idea of where these formulas are coming from. When we're looking at center of mass, the idea here is that we could have some sort of a object that has varying density and kind of a strange shape to it. The center of mass is going to be that balance point on the surface that if we could hold it up on a small little point, it would stay balanced at that point. So we could have a picture that looks something like this. So say I have a kind of surface that looks like this. And on this surface, I could have some kind of a varying density. So depending on where I am on the surface, I have a different density. And when we're talking about center of mass, what we want to find is a point so that if I were balancing this surface on this point, that it would stay flat and level. So according to this image, we would have and suspect that the density over on this side would be significantly larger than the density over on this side if that balance point was at this coordinate on the surface. The key thing to maintain, the most important thing to bear in mind here, again, is that varying density is going to result in a varying mass. But here, we're talking about varying mass at a point. And when we're talking about masses or surfaces, we're always wanting to refer to kind of outputs of the function. And so here we're saying, well, if I'm at a particular value x comma y, that's going to be associated to a certain density and a certain mass. Here I could look at this point, it's going to result in a different density and a different mass. And so what we have to account for, so we need to account for the kind of pull of gravity. So again, in this case, we end up having that there's going to be more of a pull on this side because we have that the mass over on this side would be larger as opposed to this side over here. And we're going to account for that pull in the x and y directions. And the way that we're going to do that is by looking at what are known as the moments to help us find this center of mass. So our definition here is that if we are considering a lamina d with a density function delta of x comma y, if we want to find the center of mass x bar y bar, we're going to find that by evaluating these expressions. So we have a double integral over d of x times our delta function divided by the double integral of the density. This double integral of density is always going to equal the mass of the entire lamina versus the top portion with our integral with x and delta. This is what we are going to call the x moment. And same thing here, this integral is going to be what is known as the y moment. In this example, we're given a density function delta of x comma y given by 6x plus 6y plus 6. Here we want to find the center of mass of the lamina that has this density function. When we are defining this lamina by the triangular region bounded by the x-axis and the lines x equals 1 and y equal to 2x. I'm going to go ahead and graph this region to help us understand what's going on here. So if we plot this region, we're going to have, here is my line of y equal to 2x. And we're bounding with x equal to 1 as well. So here that is going to be this line. So there's my x equal to 1. And also bounding by the x-axis means that the total region that I'm wanting to consider is this region here. So this is the region D that I'm going to be integrating my function over. So in order to have the center of mass, the first thing that we need to figure out is the total mass. So we're going to need to find our mass m, which is apparently going to be the double integral over this domain D of our density function delta of x comma y. And this will be dA. We can simplify this. So we have that our density function is given by 6x plus 6y plus 6. And now we need to integrate this function over our domain D. So we're going to have to set this up. To set it up, we can go ahead and return back to our methods of setting up double integrals over general regions and see that if we integrate with respect to our y value first, we're seeing that our y values are always going to be varying between 0 and the top value of this line, which is always going to be 2x. And we're going to be taking these orange vertical lines for values of x between 0 and 1. So in total, we'll have our limits of integration as such, where we are first integrating with respect to y, and then integrating with respect to x. Pause the video and evaluate this integral. I'll be back with it all done when you come back. Evaluating this integral gives us a final value of 14 for the mass of this lamina given this density function. Now that we have the mass of the lamina, we can go ahead and figure out what the x moment and y moment happen to be. So here, what we need to figure out at this point is we've got our x bar is going to be equal to, we're going to have 1 over 14 times the integral, double integral, over the region D of x delta of x comma y dA. And we're also going to have that our y bar is going to be very similar, but instead of evaluating x delta of x comma y, we are going to be evaluating y of delta of x comma y dA. And the process is going to be very similar. From here, what we have to do is evaluate these integrals individually, pause the video, and give this one a try. After a whole lot of integration and anti-differentiation of these relatively straightforward polynomial functions, we end up having that our x bar has the value of 10 over 14, and our y bar has a value of 11 over 14. That means that our center of mass is going to be at the coordinate 10 over 14, 11 over 14 for this particular lamina. The second application of double integrals is to find surface area of multivariable functions and multivariable surfaces. Unfortunately, this, in order to really justify it, requires that we have a real understanding of vector-valued parametric functions. We looked a little bit at this when we were dealing with lines and planes, but generally, this is something that you wouldn't really be able to fully understand until you took a course in vector calculus, which is being offered in the fall, not by me, but if you want, you can take that class. It's essentially calculus 4. In there, you can prove that the surface area of a multivariable function can be evaluated by finding this integral. So this looks a little bit weird. It's the square root of, here we have the partial derivative with respect to x the partial derivative with respect to y, and we're evaluating this interval over a region D where our partials have to be continuous. From here, we're just going to apply this formula to find surface areas of particular functions. And in the case that we're going to look at, it's just going to be the surface area of a sphere, which is a formula that we know, but maybe something that we've taken for granted and haven't really known where and why that formula works. So a sphere is technically not a function. The upper half of a sphere is. And since spheres are symmetrical, we can go ahead and find that the surface area is going to be twice the surface area of one of the halves. And that's how we're going to set this problem up. So if we go ahead and try to graph what our surface is looking like, we know that we're dealing with a sphere of radius r centered at the origin. So the surface that we are actually trying to find, and if I go ahead and do this. So let's go ahead and move this here and now give this a little bit of dimension. So now this looks like it has a spherical shape to it. We're saying that the radius here is going to be r. And in our instance, we can just look at the upper half of this sphere. So we know that the sphere is going to have the equation x squared plus y squared plus z squared equal to r squared. We can solve for the variable z and give us the upper half of the sphere. So we're going to have that z is going to be equal to the square root of big R squared minus x squared minus y squared. Here is going to be the top half. So if we want to find the surface area here, we're going to have that S of A is going to be equal to 2 times the upper half. So here we're going to be integrating over some domain D. We'll figure out that in a bit. And we're going to take the square root of 1 plus the partial derivative with respect to x, all squared, plus the partial derivative with respect to y, again, all squared, and then taking this dA. We can find the partial derivatives individually. So we'll have that f sub x of x comma y is going to be, taking partial derivatives here, we'll end up getting that this should be negative x over the square root of r squared minus x squared minus y squared. I encourage you to verify this on your own. And then for our partial derivative with respect to y, we're going to have that this is very similar, just with a negative y in the numerator instead of that negative x squared. So here are our partials, and now we can substitute these into our equation for the surface area. So we'll have S of A is going to be equal to, we'll have 2, and then we're taking again this integral over a region D, and after a little bit of simplification, we'll end up with 1 plus, we'll have x squared plus y squared, all divided by r squared minus x squared minus y squared. Takes a little bit of algebra to get there, but it's not all that bad. And now here we're taking dA. The question now is, what domain are we integrating over? And in this case, we want to focus on, for what values of x and y am I actually getting points on my surface? And that's going to happen in this region here. So what we want to do is we want to translate that region from 3-dimensional space into 2-dimensional space. If we do that, what we're going to end up with, okay, well, we've got our XY coordinate axes here. And we're going, and I don't like how that looks a little sloppy. So let's make that look a little, looks even sloppier. Let's make that look there. There we go. So we've got our X, we have our Y, and we have our circle here. So that circle is going to be the projection of the top half of the sphere down onto the XY plane. And this circle, we know, has to have a radius of big R. So because we know that big radius, now we can end up seeing that our domain is a circle. And so integrating this particular function is probably going to be better done in polar coordinates. In order to switch to polar coordinates, we can recognize that our domain D here is going to be, in terms of r and theta, we have that our radius r is varying between 0 and this big R, while our theta is going to be varying between 0 and 2 pi. This is our domain D. We can change our surface area integral to be in terms of r and theta. After converting into polar coordinates, this is the integral that we end up with. And I know that this looks gross initially, but I promise after a little bit of simplification, you'll see that it turns out to be a whole lot nicer. We can see that we've got an r squared cos squared plus r squared sine squared in the numerator. And because cos squared plus sine squared is equal to 1, we can see that this integral, the inside of the integral ends up simplifying. We have 0 to 2 pi. We have 0 to our big R. And inside, we're just going to end up with, first of all, we have this R from converting into our polar coordinates. So that's going to go there on the outside. And inside of our square root, we end up with 1 plus, we're going to have an r squared in the numerator. And then in the denominator, we're going to have that big R squared minus little r squared. And then this is all taken for dr and d theta. We can then move on a little bit more. So we'll again have the integral from 0 to 2 pi, the integral from 0 to r, and then simplifying again the inside of the square root, we have our r on the outside, and then on the inside, we're just going to be left with r squared, big R squared, divided by r squared minus little r squared. So that's getting a common denominator and bringing everything together. So then we have our dr and our d theta. To evaluate this integral, notice that we have our r squared here in the denominator. We can do a basic u substitution here. I recommend taking our u to be equal to r squared minus little r squared, so that our du is going to be equal to negative 2r dr. We can make this substitution and evaluate this integral in the standard way. We'll end up getting that the surface area is going to be 4 pi times big R squared once you evaluate this double integral. We're now in the final stretch of the course where we're going to be talking about triple integrals. When we were dealing with double integrals, we were integrating a function of 2 variables. That function of 2 variables existed in 3-dimensional space. It was a surface in 3D. We integrated over a region in the xy plane that was some sort of an area. So we integrated over an area to get a volume. Now when we're talking about triple integrals, that's not going to be as easy to visualize and put into a geometric interpretation. When we're talking about triple integrals, we're dealing with a 3-variable function. So my output is in the 4th dimension. I can't graph what this looks like. I can, however, understand that the domain is somewhere in R3. It is a volume in 3-dimensional space. Those are the inputs that I'm putting into my function that gives me an output in the 4th dimension. To help visualize this a little bit, I want to first look at a region in the 3-dimensional space that could potentially be a region of integration for a 3-variable function. In order to do that, I'm going to have to draw something. It's going to take me a little while to draw it, so I'm going to go ahead and pause myself here, generate the picture, and come back. The region given by this set consists of x values between a and b, y values between c and d, and z values between p and q. Graphically, that would correspond to the box that I've plotted here, where I have a, b for my x's, c, d for my y's, and PQ for my Zs. Everything that's going to be inside of this volume, these are all going to be the possible inputs into my function. So when I'm trying to understand a triple integral over some region in three-dimensional space, I need to understand what are the possibilities for all of the x comma y's that are inside of this volume. So if we want to say evaluate the triple integral over this box B, I'll be using this notation consistently for triple integrals over boxes, so those rectangular regions, where we're looking at f of x, y, z. Here, we're trying to integrate over something d something. When we were in triple integrals, we had dA. We were integrating over an area because our region was an area. Here, our region is a volume, and so we're going to be integrating over a volume. And what do those volumes look like? If we go ahead and zoom into the bottom corner of our volume here, I can see that this big volume is being made up of smaller, tiny volumes. So this is what I'm going to call my tiny volume, dV. And dV is going to consist of the dx, the change in y, dy, and a change in z, dz. We're going to have that change in our y. So here we get dy. Here we have dx. And then for our top bit here and our height, we end up having dz. We're going to take all of these tiny little volumes so that we end up having an iterated integral, an iterated triple integral in terms of x, y, and z. We can integrate with respect to x first, so say dx, dy, dz, so that my x values would be varying between a and b, my y's between c and d, and my z's between p and q. Fubini's theorem holds for triple integrals. So we can also have the triple integral of f of x, y, z, of starting off with, say, dy, dz, and dx, my y varying between c and d, my z's between p and q, and my x's between a and b. So here, applying Fubini's theorem to give us this equivalence. Trying to evaluate triple integrals over general regions is going to be way more difficult, but we'll work with this nicer case first. Evaluating triple integrals isn't actually all that bad. The challenge with triple integrals is the setup. So let's go ahead and look at just an example of evaluating a triple integral before we throw ourselves into the deep end of setting one up. Here we're looking at wanting to calculate this triple integral where we have a box region in three-dimensional space. We're given our box, and so we can set up this triple integral. Here we have that we're wanting to evaluate, again, triple integral over our box region B. It's a box because I have constant values for my x, y, and z. So here we'll have that 3x squared y sine of z dv. And we can set this triple integral up in whatever order we want, but there is usually going to be an easier order to start with. And in this case, I'm going to go ahead and start off evaluating in terms of dx, and then we'll do dy, and then we'll do dz. Our x's are going to be varying between 0 and 1, our y's between 2 and 3, and our z's between 0 and pi. And we evaluate this in the exact same way we would have before. We're going to focus on the inside part with our first variable, in this case, x. And so we'll end up having that this is going to be equal to, we'll have the integral from 0 to pi we'll have the integral from 2 to 3. And integrating this with respect to x, we're just going to be left with, we'll have an x cubed y sine of z evaluated from 0 to 1, and we'll have our dy and dz on the outside. Evaluating this a little bit further, we're going to have the integral from 0 to pi, the integral from 0 to 2 of, we'll just be left with y sine of z dy dz. Repeating this process again, we're now just left with a double integral, something that we're familiar with evaluating. So here we can go ahead and say we've got 0 to pi. I have y sine of z dy as the integral that we now want to focus our attention on. So that is going to give me y squared over 2 sine of z evaluated from 0 to 2, and then my, 3 to 2. I don't know where I got that from. So 3 to 2 for those. 2 to 3. And then we have here 2 to 3 of this dz. And then evaluating this after a little bit of simplification, this will give us the integral from 0 to pi of, we should end up having 5 over 2 sine of z dz, which is going to give me negative 5 over 2 cos of z evaluated from 0 to pi, which in the end is just going to give me a value of 5 for this triple integral. Triple integrals, setting these things up is hard. Visualizing these is hard. This is not easy, and it's going to take a lot of time for you to get used to. So just be patient. I've got a step-by-step process to take you through understanding how to set these integrals up. So again, the key thing here is that when we're integrating over a box, it's not going to be that bad. We have a nice iterated integral where our values of between x, y, and z are all fixed. That's always going to be nice to deal with. The not so nice situation is when we have a general region that is not a box that we are integrating over. The first step to always make your life a little bit easier with these problems is to make a rough sketch of the region. So in this case, we're trying to evaluate this triple integral, and I honestly don't care what this triple integral is. All you really need to care about is figuring out how you're dealing with this region. That's where 90% of our time is going to be spent. So in this case, we need to just always, whenever we're dealing with a triple integral, make a rough sketch of the region that we are working with. So here I've got my z, I have my y, I have my x, and we can notice that this is a plane. We are definitely bounded by the line x equal to 0, or the plane x equal to 0. So that's going to be bounding here, the plane y equal to 0 bounding here, and z equal to 0 bounding there. And then we have this z equal to 2 minus 2x minus y. We can make a rough sketch of this. This is a plane. We can notice that we have an output of 2 when our x and y are 0. When my y is going to be 0, we can end up getting that our z is going to be 0. We're going to get an output of 2. And when our y is 0 and our z is 0, we're going to get an output of 1 for our x. So the surface that we're looking at is going to look something like this. But again, this is something in just a surface in three-dimensional space. We need the volume. And the volume is going to be found by looking at everything inside here. So here, if I just kind of color this in, you can maybe see a bit more of this volume. So we want everything within this kind of triangular prism volume. We now need to figure out where we're entering and exiting this volume. Remember when we were looking at our double integrals, like here, we wanted to think about, okay, my x's are varying for certain values, and then we would see how our y was varying. And these lines are what we now want to emulate, but in this three-dimensional surface. So here we can look at which lines parallel to the z-axis are going to enter and exit this region E. And I'm going to go ahead and label that by some orange lines. So if I go ahead and look at this point, right, if I'm traveling through this volume, I'm going to be entering always at z equal to 0. So I'm always going to enter at z equal to 0. And then I'm going to fly through the surface, and I'm going to exit at some point. And I'm going to exit where? Well, I'm going to exit through the plane. So my exit point is always going to be z equal to 2 minus 2x minus y. That is going to be true regardless of where I am on this surface. Sometimes it'll be a shorter change, other times it will be a larger change. But these are the enter and exiting points for all of the points at the bottom of the region. This helps us out because remember, we're trying to evaluate the triple integral over this region E of y dv. We know that this dv is going to be in terms of our changes in x, y, and z. And here we can see that the first variable that we're going to be integrating over here is z. I'm looking at how my z is changing, and it's changing from 0 to 2 minus 2x minus y. So we can rewrite this integral as it's still going to be a double integral, but the inside here is going to be the integral from 0 to 2 minus 2x minus y of y dz, and then on the outside, I'm going to have either dy dx or dx dy. Let's just deal with dA for now. These enter and exits are going to happen for all points in this shaded green region. And that region I'm going to call the region D. So here, my region D is the projection of my volume down onto the XY plane. So here, my region D is the projection of E onto the XY plane. And now that we've set up our integral in terms of Z, we're just tasked with evaluating this double integral over a domain D. The next step in this process is to make a rough sketch of the projection of that surface E down into the XY plane. This is going to happen when we have that our Z is equal to 0 and our Z is equal to 2 minus 2x minus y. Setting these equal to each other, this is going to give me that 0 needs to be equal to 2 minus 2x minus y, which is the same as the line y equal to 2 minus 2x. We can then sketch this in the xy plane. So here we have our x and our y. And to keep our colors consistent here, we have this green line representing the intersection of our plane in the xy plane. Note that we have that our x-intercept here is going to be at x equal to 1, whereas our y-intercept is going to be at 2. This is the exact same green region that I highlighted in the first picture. It's just that instead of viewing it in three-dimensional space, we're viewing it in two. Now we're ready to set up our triple integral in full. So here we were again trying to evaluate the triple integral over the region E of y dv. Our work on the previous slide let us know that we needed to set this up as a double integral of the integral from 0 to 2 minus 2x minus y of y dz, and then our dA. So the problem now is to notice and figure out what the limits of integration on these outside integrals are going to be. And we can set it up in the exact same way. We can recognize that our y values are going to be varying between 0 and whatever this curve is. And thankfully, we have that this curve is given by 2 minus 2x. So this will end up getting rewritten as we'll have our integral from 0 to 2 minus 2x minus y of y dz. Our y's are varying from 0 to the top curve. So we'll have 0 to 2 minus 2x for our changes in y. And lastly, we have that our x values are just varying between 0 and 1. So for that dx, I have 0 to 1 as my limits of integration. Note that this was just one way to set it up. On the next slide, we're going to do the exact same problem, but we're going to set it up instead of starting with z, we'll start off with another variable. So here we're dealing with the exact same limits of integration in the sense of the same volume that we're integrating over. It's the exact same region, E, in three-dimensional space. But here, we're going to set it up so that our first variable of integration is going to be the y variable rather than the z variable. So when we're trying to figure out that setup in the y variable, we essentially need to figure out where we're entering and exiting when we're parallel to the y-axis, just like we were entering and exiting parallel to the z-axis. We got to do the exact same thing, draw that sketch, and find out where we're entering and exiting. I'm going to take a moment to draw this out so as not to waste time in the video. Okay, here's our region E, same thing, but now instead of thinking about entering and exiting this way, we're wanting to enter and exit parallel to the y-axis. So my entrances are going to happen in these directions. The first place that I'm going to enter through is going to happen over here. So I have, this is where I'm going to be entering from, and it's also going to be where I'm going to project my entire surface. So here we can see that we are going to enter and exit in this way. So here I've got my enter and exiting lines in the same kind of way, where we can see that we are going to always enter where our y is equal to 0, and we're always going to exit here in the same idea. We exit through the plane, but I don't want to have it in terms of my z value. I want it to be in terms of y. So we exit through the plane, z equal to 2 minus 2x minus y, but that's going to be the same as y equal to 2 minus 2x minus z. My entrance and my exit are in terms of y rather than z. Now that we have our entrance and exit points, we want to go ahead and set up this triple integral in the dy, dz, dx order. Note that we've already dealt with the y. We just need to figure out the dz and dx. The projection strategy is going to apply here as well. So we're going to, instead of projecting down onto the xy plane, we are projecting on to the xz plane. And what we're going to end up with is something very, very similar, where I have the value of 2 for my z, a value of 1 for my x. And so the region that I have there highlighted in 3 dimensions is here in 2. And we can set things up in the exact same way. So we're going to have the triple integral over this region E of y dv. We've already set it up in terms of the region D of, we can see that we're going to be varying for our dy's from 0, and I'll highlight that in orange to keep things consistent, to our 2 minus 2x minus z. And then I need to integrate over our areas dA. Now we're in the place where we need to set this up as a standard double integral over a general region. 0 to 2 minus 2x minus z gets taken as our dy. And again, we're wanting it in the dz and dx order. My x's are going to be varying just between 0 and 1. So I know I'm going to get 0 to 1 as my values there. But then for my changes in my z, we're looking at, and I'm going to keep this as a different color, we're going to have that our values are changing from always z equals 0 to this line. So we're going to have 0 to whatever the equation of this line is, which can easily be found to be z equal to 2 minus 2x. So there we'll end up having 2 minus 2x as our top limit of integration for the dz part of the integral. Here's another example, and this one's going to be substantially harder to visualize and to graph. Here we're looking at the solid region E above the xy plane, bounded by the paraboloid given by this equation here, and the plane x equal to 4. First things first, we're going to want to draw a rough sketch of E. I encourage you to pause the video, draw this sketch, and then I'll have it done when you come back. This is my best attempt at drawing this region E. The key here is to recognize that technically the paraboloid goes on infinitely, but we're cutting it off at the plane x equal to 4, and we're also only looking at above the xy plane. So the total region that I'm wanting to consider is given by this filled region here. Now we're wanting to set up this integral in the dx, dy, dz order. There are lots of different orders you can do, but we're going to focus on this order first. When we're doing this order, it means that we're going to enter and exit through lines that are parallel to the x-axis. So I'm going to be entering and exiting this way through my surface. Okay, I'm going to use a really light yellow color to represent where we are doing this entering and exiting. So I can see that I'm always going to enter through the back, and then I'm going to come through my surface and exit. I'm going to enter eventually, and then I'm going to exit eventually. So if we want to set up where we are entering and exiting, I think the easier one here is to see that when I come through this surface, I'm always going to exit when my x value is equal to 4. So we can always exit when x is equal to 4. Where we enter is a little bit trickier to find. We're going to enter for some value of x, which is going to be equal to the point on the surface. Sometimes that point is going to be far away, other times it's going to be a little bit closer. But that entrance is always going to happen at x equal to y squared plus z squared. Now that we have this, we have a rough understanding of what this triple integral is going to look like. We're going to have that the integral over the region E of y squared x dv can be written as, we'll have the double integral over some region D, which we'll figure out in a bit, of, we'll have our entering at y squared plus z squared, and we have that we're exiting at x equal to 4. And that's going to be this y squared x dx, and now we need to figure out what area we're integrating over. In order to finish things up, we're going to have to project our surface onto the YZ plane. So I'm going to take this and I'm imagining squishing it and pushing it to the ZY plane to think about what kind of shape we end up with. If we do that, we can see that we'll just end up with this semicircular region. I'm going to go ahead and draw the entire region just because I think it'll be a little bit easier to visualize. So bear with me as I draw this. So here is our region, and again, we're really only worried about the upper half of this circle because of the fact that we're only looking at the region above the XY plane. So here is the region that I am trying to set up my other limits of integration for. We know that the radius of this circle is going to be 2 because of where we are slicing this paraboloid. So note that we're going to have that this side of the circle is going to be given by the equation y equals the square root of 4 minus z squared, whereas this side of the circle is going to be y equal to negative square root of 4 minus z squared. So here then we can see that we're going to be setting up our domain. Because we're looking in the dy dz order, we're going to have our values of z are only varying between 0 and 2, but we can figure out what our y's are changing as. So here we're going to have that triple integral. We'll have y squared plus z squared to 4. And then we're going to have the y squared x dx dy dz. Our y's are going to be changing from this side, so our negative square root, over to that positive square root. So there we have that our limits of integration will have the negative square root of 4 minus z squared, and then we'll have positive square root of 4 minus z squared. And for our values of y, because here we're looking at y, and we have z, we can end up seeing that we're going to have our y values varying from -2 till 2. Here we're going to set it up the same region, but instead of setting it up in the dx, dz, dy order, we're going to be setting it up in the order dz, dx, dy. So rather than entering parallel to the x-axis, we're going to be entering parallel to the z-axis. I'm going to go ahead and use green to label this entering and exiting. So here again, we need to figure out where we are going to enter and where we are going to exit. And again, this has to be done on the previous image. If we're flying through the surface, we are always going to be entering at the same value of z. We can easily see that we're always going to enter at z equal to 0, and then eventually we're going to fly out the top of the surface. Same thing, entering at z equal to 0, and then exiting out through the top of the surface. In this case, we can see that we're going to enter at z equal to 0. And we know, remember, that our surface was given by x equal to y squared plus z squared. So solving for z, we have that z is going to be equal to plus or minus the square root of x minus y squared, where the plus part gives us the upper half, the minus part gives us the lower half. So we're always going to be exiting at z equal to the square root of x minus y squared. This gives us our places to enter and exit, and now we need to set up the rest of the integral by again looking at that projection. Here we want to take our surface and we want to project it down onto the xy plane. And if we project, we're seeing that we're getting this shape down on the xy plane, which I'll go ahead and draw on this next slide. By projecting that surface down onto the xy plane, we can notice that we get this kind of shape. Again, here we see that the long part of the parabola is changing with respect to x, and so this is the shape that we end up getting. It's important to note what the endpoints are here. So if I pull this down, remember that we're always splitting at x equal to 4. And so now we need to set up what this region is for our limits of integration. Okay, so now that we have this, we can do a little bit of algebra here and recognize that here I'm going to get an output of 2 for my y and -2 for my y. We're integrating in the dz, dx, dy order. So my lines that I want to figure out how they are acting through this surface are going to happen in this direction. So here I have these changes in my x. That is, we can set up our triple integral to b. We know that we have the limits of integration for our z going from 0 to the square root of x minus y squared, so that I have this y squared x dz and then dx dy. My x's are always going to be varying from this value to this value. The question here is, what is the equation of this parabola? Well, this parabola is going to be happening when we have that our z equals 0 and we have that x equals y squared plus z squared. So here we're only going to end up with both of these happening, we have that our x is going to equal y squared. So we're always going to be entering at x equal to y squared, and we're always going to be exiting at x equal to 4. So we're going to have our entrance at y squared, and we're going to have our exit at x equal to 4. And we're going to be taking this for values of y between -2 and 2. Last but not least, we're going to do the setup of this exact same region in the dy, dx, dz order. Pause the video and give this one a try for yourself. It's important to get a decent handle on these setups. I'll go ahead and work through this and then walk you through the solution. So just to set things up again, when we're trying to set up the dy order first, it means that we're going to be entering and exiting parallel to the y-axis. So it's probably helpful to reset up our curve. Instead of writing it in terms of x equals, let's write it in terms of y equals. So we have that y is going to be equal to plus or minus the square root of x minus z squared, where that plus half is going to be the side over here, and the minus half is going to be the side over there. So what we end up having here is that we can see if I'm entering and exiting through this surface, I'm always going to be entering, so again, from the smaller values to the larger values of y, I can see that my entrance is going to happen on the negative side, and I'm always going to exit on the positive side. So here we end up having our entrance and our exit going from the minus to the plus side of the surface. This allows us to write this, so entering from negative, we'll have the x minus z squared, and then exiting onto the positive x minus z squared. So we have our entrance, we have our exit, and again, we need to look at that projection. When I project this entire surface onto the zx plane, what I end up with is this portion here, changing in x and z. That is graphically represented by this region here. And again, we're wanting to look at our changes in x. Here, we can see that, first of all, the easier one to figure out is that our z is going to be varying between 0 and 2. That's where I'm going to be taking those slices. So I know that this is going to go from 0 to 2 for my z's. And then we need to figure out how our x's are varying. We can notice that this equation of this line here is happening again when our y is equal to 0 and our x is equal to y squared plus z squared, which, setting these equal together, is going to give me that my z squared is equal to x. We are going to enter at our curve, which is x equal to z squared, and we're always going to exit at x equal to 4. So that gives me that I'm going to enter at that z squared, and I'm going to exit at x equal to 4. This concludes setting up the iterated integral in all three possible ways. This example is particularly difficult to draw, so I've taken the time to draw it in advance. Here we're trying to again set up an iterated integral where we have our region is bounded by the two parabolic cylinders given here in blue and in pink. So we have this 2 minus x squared and z equal to x squared as our two parabolic cylinders. We're then going to cut it off at y equal to 0 and via the plane of y equal to 4 minus z, which I have labeled here. The same strategy applies where we need to figure out where we are entering and where we are exiting. In this case, it's probably easiest to go ahead and set up the integral in terms of our variable y first. So we're going to have this over some region D, and we're going to integrate over x, y, z, dy first. And then we'll go ahead and figure out that setup for dA. If we want to figure out where we are exiting and entering this surface, again, we're starting at small values of y and then going off to big values of y. We can note that we're bounded by this y equal to 0. And so we're always going to be entering at y equal to 0. Every single time, that's where we're going to be entering. And so we can see, or maybe it's a little bit harder to see here, that we want to go ahead and enter at y equal to 0, and we're going to exit through the plane. So we enter, we exit, we enter, and we exit. So here we have that entrance at y equal to 0 and our exit at 4 minus z. Now comes the point where we need to go ahead and project this onto the xz plane. So that projection here is a little bit harder to visualize once again. So projecting here, we have our zx plane. So here's my x and here's my z. My top curve is the curve there in pink. So here I've got this curve. And then at the bottom, I have the parabola of z equal to x squared. So we have z equals x squared, and we have our top of z equal to 2 minus x squared. This is the region that I am trying to integrate over. So here's the region that we have to figure out the bounds for. Setting these two equations equal to each other, we'll end up having that 2 minus x squared equals x squared, which means that x is going to have to equal plus or minus 1. This gives us points of intersection, -1 and 1, that'll help us once again set up that integral. In this case, it's probably going to be easier to look at how our change is happening in terms of our z values so that our integral is going to be set up in terms of the order of, we know we have that 0 to 4 minus z, we have x, y, z, we know we're starting with dy, and going in this vertical direction means that I'm going to be setting it up in terms of dz and dx. Here we can see that our z values are going to be varying from x squared all the way up to 2 minus x squared. So here, keeping those colors the same, we have x squared to 2 minus x squared. And the values of y for which we are taking these vertical lines are going to be varying from -1 until 1. So we have those as our limits of integration in terms of x, and we have a final iterated integral representing the volume that we are integrating over. Just as we used double integrals to evaluate area, we can use triple integrals to evaluate volumes. In this instance, we're trying to find the volume of the region between the two paraboloids given by these two equations. I've taken the time to go ahead and graph these surfaces so that we can see the region that we're trying to find the volume of. Now that we have this, we can go ahead and see, well, our volume is going to be equal to, as we had before, whatever region E we're looking at of 1 dV. The region E that we're trying to work with is just the surface itself. We are not integrating any other function. We're just integrating over the surface to get the volume, and over and through the surface because we're going to have everything in between. So we need to figure out where we're going to enter and exit this surface. So the easiest direction to go here is to recognize, first of all, that if we are coming through lines that are parallel to the x-axis, we're going to be entering through here. If I'm traveling this way, I'm going to enter through my first paraboloid. I'm going to come all the way through, and I'm going to exit out the second paraboloid. I'm going to enter, and then I'm going to exit. So we can see that our entrance is going to happen at y squared plus z squared, and our exit is going to happen at 4 minus y squared minus z squared. And again, this is of 1. And then here I've got my dx, and then I'm going to have the remainder here be a integral in terms of dA. Now that we have this written out, we can go ahead and set up where we are taking our other variables of y and x for our dA part of the integral. This is going to require us to project our surface onto the YZ plane. And in doing that, we can see that if I project this onto the YZ plane, what I'm going to get, so here, this circle is the circle of intersection of these two paraboloids, which is a little bit easier to recognize when we have that blue through there as well, representing that other paraboloid. So this region is the region that I'm highlighting here between these two paraboloids. So this is the region that I am integrating over. Now notice that this is a circle, so probably integrating over polar coordinates is going to be the better way to go. But let's just go ahead and set this up. Here I've got my variable y, and I have my variable z. This intersection is going to happen when we have that y squared plus z squared is equal to 4 minus y squared minus z squared, which gives me the equation of y squared plus z squared equal to 2. So I have that my radius here is going to be the square root of 2. Now that we have this, we can go ahead and set up our iterated integral. So we can end up having that this is going to be equal to, seeing how our values of z are changing. So we're going to have, and making a lot of space here is going to be important. So we're going to have y squared plus z squared. We have 4 minus y squared minus z squared. We have a 1, a dx, and then we can either set this up as dz dy or dy dz. I'm going to go ahead and use the dz dy order. Here we end up having that we are going to be taking these heights. So in this case, we're going to take our integral to go from the bottom half of the circle. So that's going to be the negative square root of 2 minus y squared, to the top half, which is going to be the square root of 2 minus y squared. And this is going to happen for values of y between the negative square root of 2 and the square root of 2. Now that we have this set up, we can go ahead and evaluate this triple integral. So here we end up getting, so I've got my limits of integration going from negative root 2 to root 2. I have my second limits, negative square root of y squared, or 2 minus y squared. I get 2 minus y squared on the top. And then to first deal with this integral, so I have the integral in terms of x. This is going to leave me with, once I go ahead and evaluate it, and I'll leave you to clean up the details, I'll have 4 minus 2y squared minus 2z squared, and then I'll end up with dz dy. At this point, you might be looking at this and say, wow, this is going to be absolutely awful. And you're entirely correct. Normally, what we would do here when we have a region that is circular is that we would change it into polar coordinates. And that's exactly what we want to end up doing here, is to change this into polar coordinates. In this case, what we end up having is that we will get, so I'm going to have an integral, and instead of having it in dz dy, we're going to have it in terms of r dr d theta. So we have the 4 here. I'm going to have a minus 2. We'll have a, so our y will be a sine squared theta, minus we'll have a 2 cos squared theta, and we'll have r dr d theta. Noticing that our r is going to be varying from 0 to the square root of 2, and we'll have that our theta is going to be varying from 0 until 2 pi. Here we can note that this sine squared plus cos squared will end up being just equal to 1. And so all we're left to integrate is that this is just going to be 4 minus 2r squared. Go ahead, evaluate this integral on your own. You should end up getting a value of 4 pi in the end.